We're going to talk about errors in testing and measurement and how those relate to biostatistics. So we're going to talk about error, sampling error, non-sampling error. So these are things that we do to introduce error. And then type 1 and 2 errors and power, those go along with these concepts, but those are actually recorded in a different video because I didn't want to make this video too long. So you can look at type 1 and 2 errors and power in a different recorded video. So first let's talk about error. So error is the difference between the value obtained and the true value for the population. We have two general categories, sampling error and non-sampling error, and we're going to talk about those two. First, sampling error. Sampling error is variation that occurs because we're studying a sample rather than the entire population. It doesn't mean that we did something wrong. The name kind of sounds like we did something wrong, but it really just means that because we're working with a sample and not the population, we're never going to get the exact population value. Even if we choose samples properly and they're representative, there's always going to be a little natural variation. So if we take a population of 1,000 people and we draw 10 different samples of 100 people, the estimates from those samples are going to vary slightly. If we've done a good job choosing our sample and carrying out our study, they'll be pretty close together, but they're not going to be exactly the same, and that's sampling error. This video by Dr. Nick goes over sources of variation, and it's a really good video. Plus, Dr. Nick has a cool accent. She's probably more interesting to listen to than me. So I'm going to go ahead and play this video.
Variation and sampling error. Hi, I'm Dr. Nick, and in this video I'm going to tell you about why statistical methods are needed. I will also explain variation and error, including sampling error and non-sampling error. Variation is everywhere. It has practical implications. That is why statistical methods are used to make sense of data. There are several sources of variation in data. Today we are going to talk about 1. Natural or real variation, 2. Explainable variation, sometimes called confounding, 3. Sampling error or sampling variation, and 4. Variation due to non-sampling error. For example, say we want to know how many texts on average a 19-year-old student sends in a day on their mobile phone. This could be useful when setting up a pricing scheme to attract students. We could ask one 19-year-old student, but we know that not all 19-year-old students send the same number of texts in a day. There is natural variation. If all students sent the same number of texts in a day, taking a sample of one student would give us all the information we need. But all students don't send the same number of texts in a day. There is variation. And this is true of almost all human, natural and manufacturing processes. There will be variation. In some cases, such as weights of medicines, the variation may be very small, but it will still be there even if we can't measure it. There are other reasons why asking one student wouldn't give us the information we need about texting habits of 19-year-old students. The men and women could send different numbers of texts, and students from different countries might have different texting habits. This can be called explainable variation. In some statistical tests, we try to find out things like the differences between groups, such as males and females, or maybe the relationship between age of the student and number of texts. We try to see what variation we can attribute to known factors. Statistical inference is the process of drawing conclusions about population parameters based on a sample taken from the population. Because of natural and explainable variation, each sample will only approximate the population. Say I took a sample of 5 students and you took a sample of 5 students from the same class and asked them about the number of texts they sent yesterday. Do you think you and I would get the same mean or average? I presume you said no, because that is correct. Because our samples will include different people, we are unlikely to get the same mean or average. That is another kind of variation. The fact that our samples included different people is the underlying cause of sampling error or sampling variation. Because we are looking at a subset of the population, we are not getting all the information about the population. And there are almost infinite different samples we could take, each with its own distribution. The term sampling error is a bit of a problem, as the word error suggests that a mistake has been made, but this is not actually the case. Sampling error arises due to the variability that occurs by chance because a sample, rather than an entire population, is surveyed. When samples are small, the potential effect of sampling error is greater, but even with a big sample we can never eliminate sampling error completely. Typically, a larger sample size leads to an increase in the precision of a statistic as an estimate of a population parameter. You might think that if we are really careful to take a random sample, we might avoid sampling error. But even perfectly random samples are subject to sampling error. Sampling error exists because a sample is not the complete picture of the population. You might think that if you take a larger percentage of the population, that will reduce your sampling error. But, strangely enough, unless the population is really small, what matters is the size of the sample, not the percentage of the population it represents. So, a sample of 100 from a population of 1 million is just as useful as a sample of 100 from a population of 10,000. The sample size, known as N, is what matters. The larger the sample is, the less influence sampling error will have on the information we get. We cannot generally measure the extent of sampling error. To do this, we would need to know the true population parameters such as the mean, median and standard deviation, as well as the equivalent sample statistics. And if we knew the true population parameters, we would not need to take a sample. But with probability modelling and procedures like bootstrapping, we can get a good idea of the effect of sampling error. Probability models underpin statistical tests like the t-test, chi-squared test and f-test. Confidence intervals express estimates of population parameters based on the information gained from a sample. Statistical tests generally require that the sample is random and unbiased, and with as little error as possible. There are many ways that the distribution of a sample may not represent the true distribution of the population. The other errors that may occur when a sample is used to infer about a population are categorized as non-sampling error. Examples of non-sampling error are badly worded questions and self-selection of sample members. Both of these can cause bias, which is a non-sampling error. There are many sources of non-sampling error, which we will talk about in our companion video, Bias and Non-Sampling Error. This video was brought to you by Statistics Learning Centre. Visit our website for more resources to help you learn. Sign up on Patreon to help us keep producing high-quality educational videos for all, and subscribe to this channel to find out about new videos as they are created.
Okay, so Dr. Nick covered that pretty well, and she mentioned a few things in there that we might use to express that variation, like a confidence interval. She mentioned standard error, margin of error, and she didn't mention the coefficient of variance, but that's another one. So we can quantify how much sampling error we have, and then we can use different measurements to express that, so that even though we know there's some sampling error, we can try to take that into account. You've probably all heard the term margin of error in regards to polls. We do a poll, say for political candidates, and we express the margin of error. So how much we feel like we're off by in that estimate. So what's going to happen to our sampling error if our sample size increases? Let's think about just using 5 participants versus using a whole neighborhood of participants or a whole city. Our sampling error is going to decrease as our sample size increases. This makes sense because the larger sample size we have, the more information we have on the population. So the closer we get to the population value, the better our actual estimate and the less error that we have. So let's talk about non-sampling error. Non-sampling error are errors that are results of factors other than that we're using a sample. So these result in bias. These also imply that we did something wrong in our design and execution, unlike sampling error, which is just because we're using a sample and not the actual population. So bias is an error in the design or execution of a study which produces inaccurate results. Something is wrong with our system, with how we designed our study. We can create an association between two variables that is not true because we did something wrong in designing or executing that study. Some common types of bias are selection bias, including non-representative. Non-representative selection bias would mean that our sample is not representative of our population. So maybe our population has an average age of 55, and our sample actually has an average age of 15. That's not going to be representative. Non-response. This means that people didn't respond to what we were looking at, and it's very comparable to the voluntary response. So people that respond to your survey are likely to be different from people who do not respond, right? And people that tend to respond, they might care about that issue more than people who don't respond. So we have to take these into account as we're designing our study and try to not just let people self-select into our study that are more interested in the issue. We want to try to get a balanced viewpoint of the population. Some types of response bias could be leading questions. So we ask a question that makes it obvious what we want the answer to be. Another one is social desirability. People are not likely to answer questions about things that make them look socially undesirable. So if you ask about things that are considered social taboos, people might not be honest about that. If you're going to ask about seatbelt usage, you're going to ask about drug use, things that they consider to not be something you would want to admit to a perfect stranger, they might not answer that honestly. You can minimize that by asking these questions in a written format or an electronic format because they're more likely to answer it that way than a face-to-face question where they're staring right at somebody, asking them, when's the last time you used illegal drugs? Okay, well, not going to want to answer that, right? But if it's written down and it's anonymous, you're more likely to get accurate results. Another type of bias is measurement bias. So here, we measured things inaccurately. Maybe we were measuring blood pressure, but our blood pressure monitor was actually off by 15 points, and so all of our measurements are inaccurate. Maybe we asked a question about food servings per week. You know, how many fruits and vegetables did you eat yesterday? And people don't understand what a food serving is. So we didn't provide a reference for them to understand what question we were asking. And so we didn't actually measure that accurately like we thought we would. Another one is recall bias. When we're asking people to tell us information about things that happened a while ago, they may or may not remember that. What they're going to default to is what their usual habits are. So I don't know what I ate for breakfast last Tuesday, but I might think, okay, on Tuesdays, I usually have a meeting at work at 9 o'clock. And so usually I stop at Dunkin' Donuts on my way to work and I grab a coffee and I grab a bagel. So that's probably what I ate on Tuesday. I'm going to default to my habit if I don't remember. So just think about that. If we're asking people to recall information, they may not be able to do that, especially if it's over a long period of time. The last type of bias is publication bias. And publication bias, this means that people are less likely to publish results that are not statistically significant. They're less likely to actually write that result and submit it to a journal for publication, and journals are much less likely to actually publish articles that don't have significant findings. So statistically significant results are 3 times more likely to get published. And like I just said, researchers may not even submit it in the first place, and journals might like to publish catchy results. All right, so here's a joke. This is where we put our non-significant results. But the problem is that then we get a biased representation of what the actual effect is. If all of the studies that showed no effect don't get published, and only the studies that do show an effect get published, it's going to look like there's a strong effect, but really there were a lot of studies that didn't support that. They just ended up in filing cabinets. We can control for bias in the design phase of our study and also during our analysis. In the design phase, we can do this by having strict definitions about what we mean by a fruit and vegetable serving, about who's allowed into our study, our inclusion and exclusion criteria. We can do this by randomizing our participants as much as possible. Even if we can't randomize treatment conditions, we can still take a sample and randomize the selection to different groups. Perhaps it depends on what we're studying, but we randomize as much as we can. Also by restriction, so we might not allow certain people in our study. Also by matching. So an example is a case control study, if you've heard of that. So we might take participants and match a person who has the disease to a comparable person who does not have the disease. So they're alike on other characteristics except for presence of the disease. We also might do blinding. That sounds really bad, but it means that the people who are interacting with our participants don't know who is in which group. So that way, if you're administering so let's say, for example, so when I got my wisdom teeth out, I actually did a drug study to get my wisdom teeth out. Fantastic, by the way. Got my wisdom teeth out. It was at a quality place. It was actually an office that I already had gone to for some other issues, and it was a well-known oral surgeon's office. And I got my wisdom teeth out for free. And then afterwards, you just have to hang out in this little room where they have recliners, and they give you a medicine, and they tell you, as soon as you start to feel pain, come back up to the counter, and we'll give you some more medicine. So you don't know if you get the drug that is already known to work, a placebo, which I doubt they did a placebo. It was probably one that they know the effect of, and one that they're testing. So you don't know which one you get, but as soon as you're in pain, you go back up and they give you a different drug. But let's say that the nurse who's handing out the medication knows who's getting which one. And to a patient who's getting the medication that is being tested, she says, okay, honey, you just come back up and tell me when you're in pain. If that subconscious tone of voice or way that she's looking at the person, those things could influence the results of the study. It's telling me that I'm probably going to be in pain pretty soon. So we don't want those people who are actually administering the medication to know who's receiving which treatment, so that they treat everybody the same and there's no effect based on just how people are being treated or how questions are being phrased. During our analysis, we can control for bias if we know that it exists by doing stratification. We can also do some standardization of our data in order to try to minimize that bias. So let's talk about confounding. Remember that a variable is an object, event, idea, feeling, something like this that we're trying to measure. We've talked about already independent variables and dependent variables. So an independent variable stands by itself and it's not changed by anything else, whereas a dependent variable depends on other factors. So now we're going to talk about an extraneous variable. This is not the variable of interest, but it influences the outcome of our experiment. So an example is the temperature in the room when you want to administer a test. So let's say we're in Arizona, we're in Phoenix, it's June, people are taking a memory test, and the air conditioning goes out. All right, all of a sudden, it's going to be like 105 degrees in that room. People are not going to perform as well on that test as they would if the air conditioning was working and it was 80 degrees, a more normal temperature. So in this case, we weren't trying to measure the temperature in the room, but it's affecting our experiment because it's affecting how people are performing on that test. On the other hand, we have confounding. Confounding is a variable that's associated with both our exposure and our outcome, and it makes our relationship look different than what it really is. So we describe an association that is true, potentially, but it's misleading about the characteristics of that. And we have some examples. So this short video goes over control variables and confounding. If you're not feeling solid on those concepts, go ahead and watch that video. This one goes over confounding in independent and dependent variables. Again, if you don't feel solid on those concepts, go ahead and watch it. So remember that an extraneous variable influences the outcome of an experiment. A confounding variable is associated with both exposure and outcome, and it makes our relationship look different than what it really is. So here's an example of confounding. So we have an exposure and an outcome, and my confounding is related to both of those. So I'm going to give you the example of the relationship between alcohol consumption and heart disease. There is a relationship between alcohol consumption and heart disease. However, there's also a relationship between smoking and alcohol consumption because it tends to be a social behavior. Not as much now that you can't smoke in a lot of public places, but this used to be much more of an issue. People, when they're drinking, would also smoke. It was a social behavior. And then smoking is also related to heart disease because smoking increases your risk for getting heart disease. So smoking is related to both alcohol consumption and it's related to heart disease. So if I don't take this into account, it's going to look like the relationship between alcohol consumption and heart disease is really strong. But I actually have a third variable that's related to both of those. And I have to take that into account in order to get the true picture of what that relationship looks like. Okay, we can control for our confounders, and we can do this in the design phase. Conceptually, we want to think through the issues. So we want to think about what we're trying to measure and what else might be related to that. So if I'm trying to study the relationship between pregnant women and their fructosamine levels and the birth weight of the baby, I need to think about what else could be related to these that I need to consider. How about pre-pregnancy weight? Pre-pregnancy weight could be related to their glucose levels because maybe they had diabetes before pregnancy. It could also be related to the weight of the infant after birth. So it could be related to both of these. So I need to conceptually think through what are all these issues that I could have variables that are related. And then I'm going to try to control for those either by randomization. So if I can randomize people to groups, then I can try to minimize some of those differences. At least it'll be evenly distributed across the groups. I can do this by restricting who is eligible for my study, and again by matching cases. So I take a person that has the disease or outcome that I'm looking at and match them with somebody who is like them on every other characteristic, except they do not have the disease of interest. So I match them to try to control for the other things that I don't want to study. During analysis, I'm going to control for this by not analyzing two variables that measure the same thing. For example, socioeconomic status and income. There's some exceptions, obviously, but for the most part, socioeconomic status and income are very highly correlated. And if I put them both into my analysis, it's going to distort my results. So I only include one variable to measure one thing. And then the other things, depending on the type of analysis, I can include my confounders in the statistical model that I build. So when I'm analyzing the relationship between alcohol consumption and heart disease, I can include smoking in the model, and that will control for it. So it's going to hold that constant and then just look at the relationship between alcohol consumption and heart disease. So that is the types of bias and error that we're going to talk about. I hope that these type of errors in measurement make sense to you. And also remember to look up the video for type 2 errors and power, because we're going to take what we've been learning about errors in testing and also about significance level, and we're going to apply that to errors that we might make when we make decisions. So make sure that you look up those videos because I separated it out just so that they wouldn't get too long.